Now we're going to take a look at osmosis. I find that a lot of students have a problem really understanding the concept of osmosis. And if you're going into healthcare, this is going to be very important to understand because osmosis is going to affect body tissues, it's going to affect blood, it's going to affect the kidneys as far as how they filter. So you really need to have a good understanding of osmosis. So let's look at the definition. Osmosis is the diffusion of water, water being the universal solvent, across a selectively permeable membrane from an area of low concentration of solute to an area of high concentration of solute. So let's look at those terms. Selectively permeable membrane or semi-permeable membrane. What is that? Now you probably have an example of one of these at home. So go ahead and think about what kind of semi-permeable membrane you have at home. Okay, having a hard time? Think about a window screen. A window screen is a semi-permeable or selectively permeable membrane. It's going to allow some things to go through. For instance, air can pass through it. I imagine some water could pass through it. It'll hold back a lot, but it'll let some through. Fine dust can still come through a screen. But what we really want to hold back are like the flies and mosquitoes and other insects, right? So that would be an example of a selectively permeable membrane or semi-permeable membrane. Usually when we talk about the human body, we're talking about the cell membranes being that semi-permeable membrane. Okay? And then solutes can be salts, sugars, proteins, all of those things draw water to them. Now, we're going to talk about solutes as sodium chloride, so that's the one solute that we'll discuss quite a bit. But either of those things, the salts, sugars, or proteins will draw water to them. So I say that solutes are water magnets. So keep that in your mind. Solute equals water magnet. And so let's see if we can visually explain osmosis to give you a better idea of how it works. Let's suppose we have a table, and on one side of the table we put one magnet, and on the other side of the table we put a whole bunch of magnets. And in the center, we're going to put a bunch of paper clips. Now these magnets are going to represent our water magnets. And you remember what a water magnet is? It's a solute. Solute is a water magnet. Okay? It's going to draw water toward it. The paper clips, they're going to represent our water. Now, if these magnets are pulling on these paper clips, which way are most of the paper clips going to go? Are they going to go to where there's one magnet on the one side of the table? Or are most of the paper clips going to be pulled over to the other side of the table where there's more magnets? Well, obviously, it's going to be pulled to where there's more magnets. So let's look at that inside of a cell. So we have water that's inside of the cell, and it has a certain amount of salt in there, sodium chloride. Okay? And so that's going to be our solutes. Now there's other things in the cell that act as a solute as well, but again, we're going to use sodium chloride as the example. And so here we have a certain amount of solutes within the cell. And in this case, we're going to have more solutes outside of the cell. If we have more solutes outside of the cell, we say that this is a hypertonic solution. Hyper meaning above or more. So hypertonic solution. So where do you think most of the water is going to move? Remember, the paper clips are the water. Is most of the water going to move out of the cell and into the solution? Or is the water going to move from the solution into the cell? Well, where's there more water magnets? Well, in this case, there's more water magnets in the solution than they are in the cell. So it's going to take those paper clips, that water, and it's going to draw it toward where there's more water magnets, where there's more solutes. And when it does that, you saw that the cell shrunk. Okay, when the cell shrinks, we call that crenation. Okay, crenation. And so basically the cell shrivels up. So let's reverse it where we have more water magnets inside the cell and fewer water magnets in the solution. An example would be distilled water, for instance. Distilled water, we wouldn't have any magnets over here. There would be no solutes. Okay, but let's say we have maybe tap water, and this has some solutes in there. Okay, if you don't have really hard water. But the soft water is still going to have solutes. If you've seen those commercials where they're testing the water filters and they take that meter and they say, oh, this particular water has so many parts per million of dissolved solids. Dissolved solids are your solutes. Okay? So which way is the water going to move now? Is it going to move from the solution into the cell, or from the cell into the solution? You have to ask yourself, where are there more water magnets, in the cell or in the solution? In this case, there's more inside the cell. So it's going to draw that water into the cell, and we say that since there's less solutes in the solution here, we call that a hypotonic solution. So again, it's going to draw that water in, and when it does, that cell is going to swell up. And it can swell up or expand to a point where it ruptures, in which case we call that lysis. So lysis is going to be rupturing and destruction of that cell. And again, that can be caused by a hypotonic solution. This is why if you give someone an IV, you do not give them an IV of just tap water or distilled water, because the cells will swell up and burst. So one more time, we have solute equals water magnet. It's important because large volume changes caused by water movement can disrupt normal cell function. And again, cell shrinkage or cell swelling. The one thing that we did mention was isotonic. Isotonic solution means they will neither shrink nor swell. That's because you have the same amount of sodium or solutes inside the cell as you do in the solution. And by the way, cells contain 0.9% sodium chloride. We call this a normal saline solution. So if you ever see an IV bag that says normal saline, then you know it's a 0.9% sodium chloride solution. So that would be isotonic. Actually, the same amount of water that's going in the cell is the same amount of water leaving the cell. And so we say that there's zero net movement of water. And again, the cell is not going to shrink and it's not going to swell. The hypertonic solution, remember there's more solutes inside the solution than there is inside the cell. And since the solutes are water magnets, it pulls that water out of the cell and causes it to shrink down and shrivel up, which we call crenation. The hypotonic solution means there's more water magnets or solutes inside the cell than inside the solution. So that cell is going to draw that water into itself, and that cell will swell up. And if there are too few solutes in that solution, allowing for more water to get pulled into that cell can actually burst and rupture. And we call that lysis. I hope that helped. And just looking at it graphically, here we have our semi-permeable or selectively permeable membrane. And again, that would represent the cell membrane. Here we can see that there's fewer water magnets, fewer solutes, than on this side, where there's more water magnets or solutes. And so what it's going to do then is pull that water through that selectively permeable membrane. Now that's going to hold back the solutes. They can't go through that membrane. And it's going to cause this side to become more concentrated and this side to become more dilute until they are equal percentages of the solutes. Okay, so I hope you understand that. This process stops when you have the same concentration of solutes on one side as the other side. In other words, we get equilibrium.